This lesson is on the kinetic theory of matter and how it is related to phase changes. The three common states of matter are solid, liquid, and gas. The way we can describe these, other than just the obvious, you're looking at it, you can tell it's a solid, is to say that it has a definite volume and a definite shape. This just means that it doesn't change. You can move it around and it keeps its volume and its shape. Liquids, on the other hand, have a definite volume. 5 milliliters is 5 milliliters regardless of what container you put it in, but an indefinite shape. This is why liquids can move or trickle. And then gases have an indefinite volume and an indefinite shape. The way the kinetic theory of matter explains this is by talking about what the particles are doing inside of these different substances. So for example, in a solid, the particles are very, very close together and they're said to be in a fixed position. This doesn't mean that they're not moving. Instead, it means that they are jittering around in a particular position. It's rather like you have a classroom full of students. Some of the students are fidgeting, some of the students are almost asleep, but they are all in their seats, so therefore they have a fixed position, just different degrees of motion. In the liquid state, the particles are still very close together. Both solids and liquids are said to be condensed phases, but the liquids are no longer in that locked position. They can slide past each other. This is why liquids flow or move, is because of the motion of the particles past each other. Extending the analogy, it's rather, if you go from a solid to a liquid state using students, it's rather like the end of the day dismissal bell rings, everybody gets up out of their seat and starts crowding towards the doorway. There's a whole lot of contact with everybody because you still have a condensed state, but you are no longer in your seats. You're no longer in that fixed position. And then gases, this animation doesn't really do it justice because the particles in a gas are really, really far apart from each other. They are much more likely to collide with the walls of the container than they are to collide with each other. There are three basic assumptions in the kinetic theory of matter. The first one is that, as we just saw, all matter is composed of small particles. This can be atoms or molecules. And the amount of space, or the volume, that the particles take up depends on the distance between the particles and not on the size of the particles themselves. This is why gases take up so much more space, because there's so much larger separation between them. The particles are in constant random motion. And then the particles undergo elastic collisions, which means that they have no loss of energy when they either collide with each other or collide with the walls of their container. To try to visualize this, just imagine you have a ping pong ball and you throw it at the wall and it bounces back at you with pretty much the same kinetic energy it had to begin with. And that's because it is an elastic collision. Now, if you take a chunk of modeling clay and throw that at the wall, it will fall back from the wall with a lot less energy. And actually, if you can measure its temperature, you should be able to measure a small temperature increase as a result of some of the kinetic energy being converted into heat when the modeling clay deforms. There is a group of students or an engineering department at North Carolina State University that pretty much every summer they will throw an 80-pound ball of silly putty off the roof of the library, which is 140 feet tall, and then they measure the temperature before and after, and there is a significant temperature increase as a result of the deformation and the restructuring of the silly putty. And then because it doesn't really fit in anywhere else, just have a definition for the absolute zero, It's the temperature at which all molecular motion stops. This is actually only really true for perfect crystals, but for what we're going to be talking about, it's good enough. The absolute temperature scale is the Kelvin scale. So absolute zero would be 0 Kelvin, which is minus 273 degrees Celsius. And if you insist on using that F word, minus 460 degrees Fahrenheit. Whichever temperature schema you use, it's pretty darn cold. So solids, there are 3 different ways that particles can be arranged to make a solid. Most of us are probably more accustomed to thinking of the first way that I'm going to talk about, which is a crystalline material. In the crystalline material, we have the particles, and they have a nice repeating pattern over and over again. It's kind of hard to see with this laser pointer thing I've got, but you can see that we got a nice hexagonal pattern. And that hexagonal pattern repeats over and over and over again as you go throughout the solid. So it's said to have long range order. The next type of solid material would be a glassy material. Now, we're not really used to thinking of glass as being a way to describe a solid, but what it is you have something that is trying to crystallize, but it's cooled down so fast that it doesn't have a chance to organize everything into this nice repeating pattern. So in a glassy material, you still have that sort of hexagonal arrangement like you have right here, but it's not repeated over and over again as you go through the solid. Just some things that you might be familiar with. Rock candy is an example of crystalline sugar, sucrose, whereas cotton candy is an example of glassy sucrose. And I know from experience that the physical properties of rock candy versus cotton candy are quite a bit different. And that's due to the way the particles are packed together in the solid matrix. And then there's the last type, which is an amorphous solid, which has no long or short range order. Don't really have an example for sugar like that. Even powdered sugar is going to have microcrystals in it. But if you think back to when we were talking about the allotropes of carbon, charcoal is an example of amorphous carbon, which is carbon atoms just kind of smushed together. There's not any real regular bonding to it at all. The graphite that is in your pencil is actually graphitic carbon. It's not true graphite, which would be atomically smooth planes, kind of like mica looks like. Instead, the graphite planes are arranged in sort of like an onion skin pattern, where you have those honeycomb pattern for the graphite, but it's been warped. So when you're writing with your pencil, what you're doing is you're rubbing off this glassy, not quite bonded properly carbon. And then diamond is your example of crystalline carbon. So this next part, let's talk about heat versus temperature and how this is related to the kinetic theory of matter. So we know that if you have a solid and you increase the amount of heat put into it, it's going to go from a solid to a liquid to a gas. Heat is defined as being the total amount of internal energy. So it's all the kinetic energy, it's the bond energy, it's all the different interactions. Since it's the total amount, this is an example of an intensive property. Temperature, on the other hand, is a measure of the average kinetic energy. So this is an extensive property. If you measure the temperature of something to be 5 degrees Celsius, it doesn't matter how much you have. The temperature is what the temperature is. So let's do a little thought experiment. Here we have 2 beakers containing 18 grams of water, so 1 mole of water, and we're going to heat them up on this imaginary hot plate at the same rate and monitor their temperatures. The first beaker is at minus 10 degrees Celsius, so it's talking about ice, and the second beaker has water at 90 degrees Celsius, so we're talking about water in the liquid state. So we're going to go ahead and put the thermometers in, turn up the temperature, and then just monitor it, and you can see that the thermometer in the ice stops changing sooner than the thermometer that was in the liquid water. So the answer to this thought experiment was that it takes twice as long to change the temperature of liquid water by 10 degrees C than it does to increase the temperature of the ice by the same amount. And that's due to an increased number of interactions that are present. And when we get to the thermochemistry unit, we will look at this some more. All right, so here is a heating curve of water. You have to remember that water melts or freezes. It's the same temperature at 0 degrees Celsius, and then it will boil at 100 degrees Celsius. So we're going to start out with the ice, and we're just going to put some heat into it at a constant rate. So you can see the solid is slowly warming up. Once you hit that melting point, rather than continuing to rise, you actually get a plateau. So now we have completely melted all of the solid. All we have is liquid left. We get another one of those slopes going up as we put more heat into it. And then once we hit the boiling point, again, you get a plateau. So we have plateaus whenever you have two states of matter present. And then once you have, you've vaporized all of the liquid, now you're just going to have gas warming up indefinitely or until it starts breaking down. The key takeaway to this is that temperature is constant during phase transitions. And that's because all of the heat energy goes to changing the state of matter. So the thing that you need to remember is that if you only have one state of matter, heat energy going into it will cause it to warm up. The temperature increases. If you have two states of matter present, you're undergoing a phase change, then the additional heat energy just goes to changing the state of matter. It does not cause the temperature to change. So if you're looking at a blank one of these, and that was not for water, you could figure out what the melting point was just by looking at the temperature of the lower plateau. And you could look at what the boiling point is by looking at the temperature at the higher plateau. And so that's about it for this one.